Hello again. This is Math 2232 coming to you from the College of DuPage, and the title of this lecture is The Gamma Function and the Laplace Transform, Examples from Applied Mathematics of Improper Integrals. As always, please be an attentive learner while watching this video. You know that the factorials are very important in infinite series and all kinds of mathematics actually. And what happened was that a great mathematician, Euler, the same Euler who had the God equation, asked the question, can the factorial function be extended beyond integers? And in 1720, he introduced the world to his gamma function, which is in fact the solution to this problem. And it extends the factorial function to the real and complex number systems. So he defined the gamma function. This is a capital gamma. This is gamma of p. And for p greater than 0, it's defined to be gamma of p is equal to the improper integral from 0 to infinity. This is x to the p minus 1. And this is e to the minus x. And this is integrated dx. So you see p is a parameter inside the integral. And so this is what a graph of it looks like, and you see it does grow very sharply, just like factorials do. But it is a continuous function, not just defined for those integers, positive integers. And it is well defined on any interval, but notice that it is actually doubly improper because when you go to 0, if p is not bigger than 1, then this is a singularity, but you go to infinity, so you see it is improper on both ends. Now, to show that the gamma function is well defined, you have to show that the integral is convergent. And to do so, the proof proceeds that you express the gamma function in the following way, and you split it up to where it's improper on this end and improper on the other end. That makes it easier to discuss it. But it's actually a lot of effort. It's about 4 pages of calculation. It involves taking limits. It includes the limit from your Calculus 1 course called the sandwich theorem, and your limit from other courses called L'Hopital's rule. It involves integration by parts and improper integrals. So you see the stuff that you're studying here really does come up a lot. Now, although this proof could be understood by COD Calculus 2 students, I'm choosing not to go through it here because it would distract you actually at an important time of the term. One of the most famous characteristics of the gamma function is that for all positive integers n, if you compute gamma of n plus 1, it will give you n plus 1 factorial. And that stems from this statement, which is proven here as well, that that is proven in the papers that I was planning on talking about. Gamma of p plus 1 is equal to p times gamma of p, which is just the same thing that happens with the factorials. And this is a recursive relationship, and this holds for p greater than or equal to 0. Now, proving this proof is another 5 pages. And although it's understandable by COD Calculus 2 students, you do know enough calculus now to understand that we're not going to spend the time going through all those calculations. But the results don't stop here just with the positive integers. And there are results where you can show that gamma of 1/2 is the square root of pi, gamma of 3 over 2 is the square root of pi over 2, gamma of 5 over 2 is 3 square root of pi over 4, and finally, a general result is that gamma of n plus 1/2, and you see we're defining it for non-integers, is it is 2n minus 1 whole factorial over 2 to the n times the square root of pi. And there are tables that applied mathematicians use for gamma functions. And here's an example of an excerpt from such a listing of a table. This really is important stuff, and it's based on many of the things that you've learned. and it has many applications in mathematics and the physical science. You can calculate volumes of n-dimensional unit balls. It will be used, the gamma distribution is used to determine the wait time for the alphath occurrence of a Poisson distributed event in statistics. It's used with the beta function, which we talked briefly about previously with Euler, and it also allows you to calculate fractional derivatives, the alphath derivative of a monomial for any alpha, an element of the real number. These fractional derivatives are increasingly important in the period in which we live. And if you take differential equations at the college page, you will encounter the gamma function in the study of Laplace transforms. It shows up in some of the Laplace transforms. And speaking of Laplace transforms, the Laplace transform is another example of an improper integral that is very important in applications. The Laplace transform is named after its inventor, who was not Euler. It was Pierre-Simon Laplace has often been called the French Newton. Newton was a Brit. And this is an integral transform that converts a function of a real variable t, and often this is time, to a function of a complex variable s, and this is often a frequency rather than a time. The transform has many applications in science and engineering. This is used in speech compression and other digital signal processing things. And it is a tool for solving differential equations, and that's where you can encounter this at the college page in the course called 2270. In particular, it transforms linear differential equations into algebra equations, which are easier to solve, and it turns integral convolutions into multiplication. For suitable functions f, the Laplace transform is defined by this integral. So the Laplace transform of the function f, and this is a function of the variable s, is the improper integral from 0 to infinity, and this is f of t. This is e to the minus st dt. So you're basically doing this transform. Although I can't go into actually using this to solve differential equations, I will talk about in general how this works. So you have a differential equation that you want to solve, but it is difficult to solve it this way. So you take the Laplace transform and you turn the transform problem into an algebra problem, not necessarily an easy algebra problem, but an algebra problem, and then you solve the algebra problem, but then you can invert the Laplace transform to find the solution to the original problem. This is very popular in electrical engineering as an example, and this is a broader math modeling kind of construct. So it's important, I think, to expose you to such things. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.